Okay, welcome back. So first I want to show you the output from Systat. And remember, I'm not pushing Systat, and in fact it's not something that I expect any of you will use, but I show it more for nostalgic purposes than anything else. And so here you have the Systat output. And notice that after you run the model, and here this is the low birth weight study, and I've told it that low birth weight is the dependent variable, and I fit the model beta naught plus beta 1 times last weight plus beta 2 times race. And then I say DC, number, smart equal 10. That's the code for Systat to tell it that we wanted it to do a risk, the goodness of fit test, calibration test, where and I don't understand the words they use here, but this is saying that you want to make 10 groups. You have control over how many deciles, essentially, to create, and this is the way to create 10 deciles of risk. So here we have it, and notice that, I should tell, before I go much further with this, I should tell a small story in that when Dave Hosmer and I developed our goodness of fit test. We of course published it in 2 different places. One was a more sort of applied paper, and one was a more theoretical paper. And in any case, we got a note from BMDP. Now, sort of to take you back to the 80s, in those days, the big players in statistical software in the world were SAS and BMDP. Systat was a very small player, and it was more like they had applications for microcomputers, but there wasn't really a respected mainframe computer program. But the big ones were BMDP and SAS. And in those days, of course, we didn't have laptop computers like this, but we had mainframe computers that essentially took up entire rooms. And when a program was installed on that computer, there was physically a magnetic disk, a large, magnetic tape, a big roll, and a computer operator in the facility would mount the disk onto the computer, and then it would read information off of the magnetic tape. But it came to the computer operators as a big, huge, think of a big movie reel, but it was bigger than that, and it contained all this information that the computer was using to do its calculations and so on. We got a letter from BMDP one day, and it told us that they read our paper and they thought that the statistic was useful, and that they were going to put it into their statistical package. And I was just beside myself. I thought this was one of the great things I've ever heard, that they were going to actually put our statistic on their program. And every day I impatiently waited for the mail to come to know when in fact the thing arrived, and then it would be mounted at the computer center. And I waited for quite a while, but every day I was just making a call, did you get it yet? And every day, did you get it yet? And it took a long time for them to get it. And finally they got it, and they mounted it. And I have to say that that was one of the worst days of my professional life, because when they mounted it and then they ran the program, we put in a test run, the statistic that was noted by BMDP was the Hosmer statistic. And after all that waiting for the program to come, it turned out they gave him full credit. But then, as it happens, sometimes good things happen. It turns out they made a mistake. So it was actually wrong. And so the program that I was disappointed not to have some share of the statistic, I was actually happy because it was not right. And then they finally got it fixed up. And so in the end, this statistic is now available in every statistical package. And you can find it certainly in SAS, and you can find it in Stata, and every other package you really can think of. This is kind of routinely computed for programs doing logistic regression. Now, the other thing that BMDP did, besides doing something wrong with the calculation, is that They did not present a table like this one in Systat that showed you the actual 2 by 10 contingency table. This is really important because it shows you for each, first of all, it shows you the cut points, and then it shows you how many people were in each cell and the expected number of people in each cell of the table. And so you can see here, this table is telling us that the first cell is created, the first decile is created of all individuals whose probability of having a low birth weight baby is between 0 and 16.785%. And in that first decile of risk, there are 2 people who had a low birth weight baby, that's the observed number, and there are 16 people who did not have a low birth weight baby. If you sum up the probabilities of y = 1 for the 18 people in the first decile, the sum of the probabilities is 2.198. So notice the observed number and the expected number is quite close. And here, and for each of these cells, the observed number and the expected number is quite close. There are some cells out here, like here you have 12 people whose probabilities were between 40.774% and 47.69%. There were 12 people who had a low birth weight baby, where you only expected 8.3. So that seems like, well, that's getting to be kind of a big difference. But still, when you take the observed number minus the expected number in each of the 20 cells squared over the expected number, the sum of those values is 7.04. And 7.04 corresponds, is compared to a chi-square distribution with 8 degrees of freedom. And the p-value is 0.53. In this case, unlike most p-values, in this case, a big p-value is a good thing. You don't want to have small p-values. Small p-values occur when the observed count and the expected count become quite different. When they're different, then the statistic gets big and the p-value gets small. So most people get excited when you have a small p-value because that means that they can reject the hypothesis and they are happily able to say something. In our case, that's not the way it works. In our case, if you have a small p-value, you have a problem. So I remember going to a statistical meeting. No, it was a meeting of the Society for Epidemiologic Research within the same year that our statistic was published. And it was the first time ever that I saw somebody present results using our statistic. And there was a young woman who was presenting the results of her doctoral dissertation, and she showed her tables and all. And then her last slide was where she showed the goodness of fit test. And I practically fainted because I'd never seen anybody do that before. And there it was on the screen. And she had the statistic, p-value 0.016. And she said, therefore, the model fits. And of course, it's exactly the opposite. If you have a p-value of 0.016, you've hit a major problem. And you really have to, at that point, figure out what to do. But clearly, a model having a p-value of 0.16 is not a good thing when you're doing model development. Okay, so you get the idea. It is a really good idea to have this table. And the fact was that BMDP didn't have the table. And it's a good idea to have the table because sometimes in this statistic, you will see a small observed number, but a really, really small expected number, and that can get you into serious trouble. So, for example, I'm going to go to the whiteboard here. So, for example, imagine that you have your 2 by 10 table, and imagine that one of the cells in the 2 by 10 table, right here, had an observed count of one person, but an expected count of 0.02. I actually have a data set where this is the case, where this is what we get. So this is not a big, this only means that it's a poorly fit covariate pattern. It's a person who actually died who had a small probability of dying. Remember, and it happens, that happens sometimes. We talked about that. But all of the other cells had bigger numbers and bigger expected counts, and so there was greater correspondence. So it turns out that if you have a cell like this, when you compute, you're computing the sum of observed minus the expected squared over expected. When you do it for that cell, the observed count is 1, the expected count is 0.02, squared over 0.02. This is approximately 50, just from that cell. So this is a really big problem. I mean, it's not such a bad mistake, and yet the statistic is huge, and this would cause rejection of any chi-square test based on 8 degrees of freedom, just from one cell, from one person. You know, you might be wise in this case to drop this person out before you did the goodness of fit evaluation, but that person is really hurting the test. Okay? And generally speaking, this rule that I talked about of having, you know, a minimum expected count of 5, you don't need that. But as long as the counts are, you know, at least 1 or more, and as long as you don't have tremendous difference between the observed and the expected count, you're okay with our statistic. The big problem comes in when you have this really small probability and any number of people in the cell. Then the statistic can actually blow up. And that's why it's very useful to be able to look at a table of observed and expected counts. Okay? So, having said that, let's take a break. And then when we come back, we will look at some more of the systat output. We'll also look at the stat output.